Got about 30 more minutes today. We'll get through as much as we can. Like I said, I'm not planning on finishing these notes today. So today, we should be able to graph exponential growth functions and graph exponential decay functions. Again, those are things I know you have all seen in your science classes, right? Exponential growth and decay, yeah, science classes, hopefully. Maybe not super recently, but I know you've done it. So here we go. In an exponential function, the independent variable is an exponent. Independent variable is usually which one, x or y? Anybody remember? X, yeah. So if you want to put a little note there for yourself, the independent variable which generally speaking is x. If you're talking about x and y, it's always x. So the x-axis variable, we're on page 357. So of the x and y variables, the independent variable is the x variable. It's the one that's going to happen no matter what, like time, right? Time happens no matter what. An exponential function has the form of f of x equals b to the x power, or y equals b to the x power, where the base b is a constant value, 2, 3, 4, 1/2, whatever you want. And x, the independent variable x, so it tells you right there, is the exponent. If something is going to be exponential growth, the value of b, the base value, is greater than 1. Again, this is stuff that you've all seen before. Whether or not you remember it might be something a little bit different, but I know you've seen it before. So for an exponential growth function, b is greater than 1. Exponential growth occurs when the initial amount increases by the same percent over a given period of time. Graphs of exponential functions have, this might be a new word, asymptotes. Anybody ever heard that word before? No? Okay. An asymptote is a line that a graph approaches. It approaches it, but it never reaches it, is what that means. So like, well, I'll show you. It's basically like something can get really, really, really close to something, but never actually get there. The thing that it never actually gets to, but it gets infinitely close to, is the thing that is called the asymptote. So let's have a look at our first example. Again, I know you have probably all graphed this exact function before. So graphing exponential growth functions, graph f of x equals 2 to the x power. Find the domain, all possible values of x. Find the range, all possible values of y. The y-intercept, where is across the y-axis, the asymptotes, and the end behavior. So the easiest way to think of an asymptote as well, when you're talking about exponential growth or decay, specifically with those things, would be where it levels off. Where does the graph level off? Now that works for exponential growth and decay. There are other types of asymptotes with other types of functions, but if we're talking about exponential growth and exponential decay, asymptotes are where the graph usually levels off. So making a table of values. We're going from -3 to +3 on the x-axis. It's always a good idea just to center your values around 0. So 3 into the negatives, 3 into the positives, all around 0. And then if you use your calculator to figure out what these values are, 2 to the -3rd power would be 1/8, and 1/8 as a decimal is 0.125. 2 to the -2 power is 1/4, which is 0.25. 2 to the -1 power is 1/2, which is 0.5. 2 to the 0 power, or anything to the 0 power, is, check the graph. When x is 0, what does y equal? 1. Anything to the 0 power is 1. And that's because 2 to the 0 power is the same thing as 2 divided by 2. 2 to the -1 is 1 divided by 2. 2 to the -2 is 1 divided by 4. 1 divided by 8. And then we go the opposite direction. 2 to the 1st power is 2. 2 squared is 4. All right. And then 2 cubed, 2 to the 3rd power is 8. All right. Great. Values of the domain. What are our possible values for x? Goes negative forever, that's going to keep going positive forever. So what's that? It goes to -infinity and positive infinity, which includes all real numbers. Yeah. So the domain here, you can just say all real numbers. The range, on the other hand, Let's go ahead and test some other numbers on the bottom end here. This 0.125. So on your calculators, go ahead and type in 2 to the negative fourth power. What do you get? 0.0625. Okay. How about 2 to the, let's say x is negative 25. So 2 to the negative 25th power. I get mine in scientific notation, which basically means that if we moved this decimal 8 spaces to the left, that would be that number. So you'd have 0.000000298,023. Yeah, x is, or not, y would be greater than 0. So these numbers never actually reach 0. So as you go to negative infinity on the x-axis, on the y-axis, you're approaching 0, but you're never actually getting to 0. So the range, y, is greater than 0. It's not greater than or equal to. It will never actually equal 0. It will always be greater than 0. The y-intercept, where is it? 1. Okay, so y-intercept would be y equals 1. Now, the asymptote. Yeah, is it a horizontal asymptote or is it a vertical asymptote? Horizontal, okay. So I'm just going to go ahead and underline that in red. And then right here, I'm just going to do a dotted line. That is the asymptote. Anytime you have a horizontal line, it is a y equals. The slope is 0. So it's all defined on the y value. So what is the y value right here? 0, yeah, y equals 0. In fact, with exponential growth and exponential decay functions, again, this is pretty specific to these types of functions, but the range and the asymptote, you will end up having the same value. All right, end behavior. As x goes to negative infinity, where does y go? So as x goes this way, y goes to where? Y is getting closer and closer to 0. Yeah. Okay. It's approaching the asymptote. The asymptote's at 0. And then as x goes to positive infinity, where's y going? To where? Positive infinity, yeah. As x goes to positive infinity, y goes to positive infinity, but we don't write plus infinity, we just write infinity. So f of x goes to infinity. So that would be the graph and the characteristics of the graph. Most of this stuff you have done before. There's very, very little new information in this, hopefully. If there is new information, hopefully it's understandable new information. So down here, this little study tip, it says you can find the asymptote of an exponential function by using a graph or a table. And we did both, right? We saw the graph here. We kind of assumed, you can make assumptions about where the asymptote is going, but you might not always be right where that asymptote is going. Sometimes it goes a little bit lower or higher than you might think, which means it's never a bad idea to run some numbers on the x-axis with the function to see where it goes on the y-axis. Because we were able to do that with our values of x. We knew that it was approaching somewhere as we went negative. And if it went below the x-axis, we would know it. But we went to negative 25 for our value of x, and it still was above 0. So we could kind of tell it was approaching 0. So there are ways that you can test it both for the graph and with the table. I would recommend a combination of both. Get yourself a visual if you think it's heading somewhere, test some values of x with the function just to verify that, because that'll give you confirmation on both ends, both graph and table. So, Zach, I'll give you a little bit of time to get that in there. And we'll go ahead and turn the page and do a little bit more. But like I said, we'll take things kind of slow today. We'll pick things up a little bit tomorrow in terms of our speed, but I don't want to throw too much at you on a day where you were working on a test. So. Hopefully most of this is looking pretty familiar so far. All right, turn the pages. This next one. Graphing a transformation. Hey, transformations. By the way, that page that was the very first page of your test, slash the page that I gave you for your notes that had all the different like exponents, cubes, and fourths and fifths and all that, also has rules for functions. And those rules for functions are just kind of the rules for functions. Transformations and translations and reflections and all that kind of stuff. Those are kind of just the basic rules. So if we were to graph this, our basic function here is 3 to the x power. So the basic function here would be y equals 3 to the x power. Our base value is 3. Our exponent is x. Now there are things acting upon it, right? We've got a -1/2. We've got a +1 at the end. We've got a +4 up with our exponent. So I'm going to grab that cover page and we'll talk about what's going on here. By the way, I don't think we've written this down yet. We have not. Let's go ahead and go back to page 357 real quick. So, because I don't see it written anywhere. I'm just making sure it's not written somewhere else. It is not. So, standard, write this down. Standard form of exponential trying to decide if I want to split this into exponential growth and exponential decay or just exponential function. I'm just going to go with exponential function. Standard form of an exponential function. And that is going to be y equals a times b to the x. A times b to the x. So the value of a is just like any other value of a that you've ever seen on a function. It determines, a is going to determine whether or not you end up having a stretch or a shrink. It'll determine whether or not you have a reflection across the x-axis. Other things that can happen, though, is you can have vertical shifts, you can have horizontal shifts, you can have horizontal reflections as well as vertical reflections. And so those are things that we're going to need to kind of figure out as we move along. So let's see. The page here. Was that? Okay. Good. All right. So here we go. Y equals a times b to the x power here. So it's a transformation, and that's what I was just showing you a second ago. It's a transformation of the graph g of x equals 3 to the power of x. So the base function here is 3 to the x power. So the a value is equal to what? So if 3 is b, the number in front of it is a. So what's a? -1/2. All right, so a equals -1/2. Because it's negative, it reflects in which axis? X-axis. Yeah, it reflects across the x-axis. and compress by a factor of what? Yeah, or compress by a factor of 2, that's fine, yeah, or vertical compression by a factor of, it's a good question. Do we say by a factor of 2 or by a factor of 1? I'm gonna say compress by 1/2. I prefer keeping the value the same as what A actually equals. That's kind of where I'm at. All right, now H and K. Think about this for a second. H and K have to do with anything that moves left, right, or up and down. Remember, H is going to be your horizontal shift and K will be your vertical shift. Let's talk about K first. K is always the number that isn't with X. So in this case, that would be the one that is not with the exponent. So what's our value of K here? 1. Okay, K is 1, which means we're translating 1 unit which direction? Up. All right. And then H is equal to, you know what? I'm going to do a different form of standard form here. So on this page here, I just want you to write y equals A times B to the, and then in parentheses, write X minus H, and then plus K at the end like that. Same idea, but I want to include H and K with this. And it looks the same as anything else that we've ever seen with H and K. It's always going to be X minus H, and it's always going to be plus K. Just like that. So because subtraction is with the standard form, and we have a +4 here, what does that mean H is equal to? -4, yeah. So we are translating 4 units. If it's negative, what direction is negative on the x-axis? Left. Good. And you can actually see that right here. If we go back and we look at the original function we had, which was not y equals 3 to the x power, is y equals 2 to the x power. 3 to the x power just means it's a little bit steeper than 2 to the x power, but it has the same basic shape as this here. So if you think about this particular function compared with this function here, it's upside down and it's been moved left and up a little bit. In fact, you can actually use, I would recommend doing this as well. You can use your graphing calculator to compare the two graphs. If the parent function in this particular situation is y is equal to 3 to the power of x, that's our parent function there, and we end up with -1/2 times 3 to the x plus 4 plus 1. We can just do a quick comparison here. So here comes y equals 3 to the x power, and here comes the transformation. And so you can actually, give yourself a visual here. It's been moved left, it's been moved up, it's been flipped upside down, and it's a little bit shallower because of the 1/2. So all the things that we know about transformations still apply with exponential functions. All right. Let's keep going. We'll do a couple more here. There's still plenty to go through tomorrow. All right, example 3, analyzing graphs of exponential functions. So let's take a look. Identify the value of k and write a function of the graph of j of x is equal to f of x plus k as it relates to f of x equals 3.5 to the power of x. Basically what it's saying is, this is your base function here. That's your function that you're starting with. And it only wants you to figure out a value of k. So there is a transformation. What kind of a transformation? Reflection? If we're only looking at k, is there a reflection? No. Is there a stretch? No. Is there a horizontal shift? If we're only looking at k, is there a horizontal shift? No. Vertical shift? Yeah. So we're only looking for a vertical shift here. So this is our parent function. Let's see what that looks like. Let's graph that. And then we'll be able to figure out what's going on. Actually, no, we won't do that because, oh no, this is j of k, never mind. J of x, yeah, so here's f of x. So let's look at 3.5 to the power of x. And see how this differs from 3.5 to the power of x. And the thing to look at here to determine your vertical shift would be, if it's only a vertical shift, look at the y-intercept. That's going to be the best way to figure it out. So where is the y-intercept of this one? At 1. Where's the y-intercept of this one? At -1. So the graph has been translated, yeah, 2 units down. So what does that make k equal to? -2. Which means the function is equal to f of x, which is 3.5 to the x power, plus k, and k is -2, so -2. That's it. It's just this function moved 2 down, so 3.5x -2. All right. Questions about transformations? Decent so far? Hopefully. All right. If you end up with questions, let me know. Let's do the next one and the check after that, and then we will leave. Yeah, we'll just finish exponential growth today, and then we'll do exponential decay tomorrow. That's a great division. Okay. So exponential growth can also be modeled by a of t is equal to a times 1 plus r to the t power, where a of t represents the amount of time after t time periods. So our exponent of t corresponds to the x-axis, but t is representative of time. So this is a specific exponential growth model. And if things are growing, they are growing over time, which is why t is specifically used here. These are just generic functions, x and y. These ones have to do with growth over time. They represent the same thing because they're going up, but this one has specifically to do with things that are growing in size over a certain amount of time, which is why we're using t. A is the initial amount, so whatever amount that we started with, that's our value of A. R is the percent of increase per time period. So percent of increase per time period. Percentages will always be translated into what kind of numbers? Like if something's written as a percent, how would we end up writing that for R? As a decimal, yeah. Percent written, write this down if you need to, as a decimal of increase per time period, and the growth factor is in the group 1 plus R. So if something is growing by 5%, that would be 0.05. But that means the growth factor would be 1 plus 0.05, which is 1.05. For example, I'll just do a really basic example. If you have $1 and that dollar grows by 5%, how much money do you have? $1.05, right? So the reason why we want to multiply A by 1 plus R instead of just R is because if you multiply by R, so if you start with $1 and you multiply by the growth rate, which is 5%, that gives you 5 cents, which would then mean you'd have to go back to the original value of 1 and then add together the amount that you've earned to get your total, which is $1.05. Whereas if you use 1 plus R times the initial amount, you can say 1 times the growth factor as opposed to multiplying by just the growth rate. Multiplying by the growth factor would be 1 times 1.05, which gives you the amount of money that you actually have. It incorporates both the growth rate and the fact that we're adding that amount to the original amount to give you your total. So instead of, it basically just skips a couple of steps. It makes it a little bit easier using that formula because you don't have to figure out the rate multiply by the original, add to the original, and repeat that process. It just puts it into one form. So, does that make sense? Hopefully, maybe. All right, let's take a look at example 4. Mr. Lopez recently won the lottery. All right, so actually, did you hear recently, like, what was it, last week? Somebody in Portland won Powerball, and it was like over $1 billion, which is insane. Great. So anyway, suppose he takes the lump sum payment and he invests $50 million into an account that yields 5% interest annually. Graph a function that models his account. Then estimate the amount in the account after 20 years. So here we go. Use the function a of t is equal to a times 1 plus r to the power of t to model the amount of money in his account. So we're just using this form of the function, exponential growth. Let a be the amount of investment in millions of dollars. We don't want to type in 50 million. We'll just type in 50 and we'll say that that's equal to 50 million. Let r be the annual interest rate when written as a decimal. Hey, it tells you right there, write it as a decimal. So if r is 0.05, then the growth factor is 1.05. Adding 1 plus 0.05 is 1.05 with the initial amount at 50 million. And then t is going to be time in years. So use a graphing calculator to graph the function, use the table feature to estimate the amount of money in the account after 20 years. There will be approximately $132,664,885.26 in the account after 20 years. So in 20 years, that money has more than doubled. And he's not added anything, it's closer to tripling. And he hasn't added any money in the meantime. He just put 50 million in and just let it sit. Didn't add any money to it. It just grew on its own to almost 3 times the amount that it started with. So, by the way, you could also, instead of using the actual graph to figure it out, you could just type in 50 times 1.05 to the 20th power. That would also give you this number here. So I want you to try the last one on the next page. Right here. On New Year's Day, Alma begins a savings plan. She saves $1 on the first day of January and increases the amount she saves each day by 1%. Find the growth factor. Then use a graphing calculator to estimate the amount of money she should save on day 180 of her savings plan. So this is the amount of money that she's putting into her savings account, not how much money she has in her savings account. But go ahead and work through this one real quick. How much money is she putting in her savings on day 180? First of all, what's the growth factor? 1.01. All right. Again, you don't actually have to use the graph function on this one. You can just type in the function and put the correct exponent in with the growth factor. How much money is she investing on day 180? I would say close, but if we're rounding to the nearest cent, this 5 here is going to round the 9 up 1 more, which will round that 9 up 1 more, which will round that 5 up 1 more. So I'd say it's going to be an even $6. All right, cool. We got less than a minute. Go ahead and pack up. We'll finish this up tomorrow.